Get rid of that. Let's go. All right, here's the next one. So I can move that out of the way. This is going to be important for we're doing today, these two questions. That's why we're doing them. And actually, there's a method to and I can write on this. So would be good. Okay, so what happens in the first step? What is the piece that's in here? What do you get? Here's your clue. So what do we get? Okay.
What would you name that?
What would I name that? Acetophenone. Mm-hmm.
So is that one that you were saying that we would?
That's a special name, and the ON is for the ketone. Okay, I'll go over ketones and aldehydes in the lecture you get later this week. Okay. All right, so what does zinc, mercury, and HCl do? Reduces the carbonyl to a, here's your clue. Okay, so what's the name of that? Okay, what is the name of the first reaction? Nope.
Acylation.
Yeah. Okay, the way you tell the difference is the carbonyl. Okay, this is actually considered an acyl group because it has a carbonyl on it. Okay, so and who were the scientists? Friedel and Crafts. Acylation. Okay, and what is this one called? Yeah. The Clemmensen reduction. You remember the reduction part? It helps you remember that it adds hydrogen to it. Okay? All right, everybody back with us? You remember those? What was the other one you could use besides the Clemmensen? What was it called? Wolff-Kirchner. Yeah, I don't know if the Wolff is easier to remember. I don't know. Okay. So when you look at your OP, meta directors, and activating, deactivating kind of thing, you'll notice that all of the activating groups are orthopara directors. You notice that? Like a little theme, because it's putting electron density into the ring, so it's stabilized when attack is at the ortho and para positions. Okay? Strongly activating groups contain a lone pair on the atom directly attached to the ring. That would be oxygen, nitrogen. Okay, those are the two main ones. Okay, but not the halogens. Okay. Strongly deactivating groups are meta-directors. Strongly deactivating groups are meta-directors. That would be nitro, CO2H, those kind of things. And many deactivating groups, not all, because nitro is a deactivating group, contain a carbonyl directly attached to the ring, because that's going to pull electron density out to that O, so you can draw resonance forms. Halogens are unusual. They are deactivating, but they're ortho-para directors. Is that like down there? Yeah, okay. I'm like, just have OP hyphen. Okay. That should help you, because you know that I can draw 1,000 directors. Okay, there's no way that you can memorize. You have to get the what's the same in your brain so that you can go, oh, that one is this director, that one is that. Okay. That's going to really help, because what we're going to do now is we're going to do those same electrophilic aromatic substitution reactions, but we're going to do them on benzene rings that have groups on them. Okay, so this first compound up there, what is the name of that? Just to help you review. Benzene sulfonic acid. Okay, benzene sulfonic acid. Okay, and then the reaction is chlorine and FeCl3. So you need to know what kind of group is on that benzene ring, and you need to know what the reaction is going to do. And then you put them together. So what is chlorine and FeCl3 going to do? What is it going to do to our benzene ring? What? Add a chlorine. Actually, it's substituting a chlorine in place of a hydrogen. Okay? So get that in your brain first. Okay? So that's what we're doing. We're adding a chlorine. Okay? Chlorine is going to go on the ring. What can you tell me about SO3H as far as its directing ability? What kind of director is that? What do you think? Well, what does it look like? It looks like this. Some of them you may have to draw them out to look at them. That's where it's attached to the ring. So what kind of director do you think it is? It's a what? It's a deactivating meta-director. Okay, so what do you think the product is going to be? What are we going to put on the ring? Chlorine, and the SO3H is telling us where it can go. Okay, so it's going to go where? Meta. That's it. It doesn't matter if you draw it on the left side or the right side. There are equivalents. Remember, all the bonds of benzene are equivalent. Okay, look at the next one now. What is this thing going to do? What are we going to put on the ring? The C double bond O attached to a methyl, not the chlorine. Okay, that part's going to leave. Okay, what is this group? What kind of director is it? It's an activating OP. Okay, so what are we going to get? You're going to get two products. It is difficult to predict which one is major unless you have a really large group like a T. Okay, so where is our little group going to go? Ortho and para. So can you draw them? Try to draw them and then I'll release it. So you see how you're doing. And it's okay if you put your ethyl on the top part. It doesn't matter. I think I was trying to give me more space on the slide. That's why it ended up. And you can write ET for ethyl too. That's okay. Capital E, lowercase t. We're not going with extraterrestrial. All right, you ready? Is that what you got? One ortho and one para. Okay, it doesn't matter which one you draw first either. It's hard to predict because sometimes the group isn't super big and there are 2 ortho spots to 1 para spot. So you kind of have that little probability entering in. All right, now look at the next one. Okay, so what's happening on this one? What is this? Woohoo. Okay, sulfonation. So what are we going to put on the ring? SO3H. Good. Okay, and what can you tell me about this group on the ring? It's a meta-director. It's a deactivating meta-director. Okay, so try to draw that product, what you think it is, and then I'll release it. We'll see how we're doing. I would draw the benzene ring for you, but I don't need to. I think it's under my box because I pasted it in from something else. The entire slide. Uh-oh. All right, you ready? Is that what you got? Okay. And you could write CO2H. There's nothing wrong with that. Okay. How are you feeling about it now? It's not you. The key is the group that's on the ring tells the incoming group where it can go, not vice versa. Okay. The group coming in has no say in where it can go. Okay. The group that's on the one that's in the neighborhood first gets to tell the new person where they can live, okay? Or in the dorm first. Okay, so what do you think about this one? Can you read them? Can you read the pictures good enough? This is that issue with the pasting. Makes them all grayed out. Okay, we're there. Okay, yep, it's E. Okay, don't try to predict between ortho and para unless you have a really big group like a T. Okay, how could you make D? Does anybody remember that? Just as a little review, since we have tests and all these things coming up. Anybody remember how to do that? Oh, how quickly they forget. All right, so what element do I need? Bromine. Do you think I use HBr? No, there's no base there. Okay, so I'm going to use Br2, but instead of Fe, what am I going to use? Do you remember this? Free radical, because you'll have a benzylic free radical, which will be stabilized by the ring. Okay, so just a little sideline there. A little extra for today. Okay, what if you have more than one thing on your ring? Here's some rules and guidelines. All right. Sometimes the substituents will direct the incoming group to the same place, in which case you're quite happy. Okay, you're pretty excited. Yeah. Okay. If not, the most activating substituent wins. So you kind of should have in your mind the order of the activating to deactivate. Okay, most activating wins. Pay attention to steric effects like a T-butyl group. And positions between 2 meta-substituents are particularly difficult to substitute because it's just, there's stuff in the way. So for example, if you have this compound. What's the name of that compound? Metaxylene. I heard a xylene back there. Okay, this spot is going to be really hard to substitute. So something is not going to go in that spot. If you wanted to put 3 things in a row, you'd have to make it a different way. All right, you ready? We're going to do some. All right, so what do you think about this one? We have para-nitrotoluene, right? Okay, so the methyl up here, since he's blue, I'll use blue. Okay, what spots is the methyl directing to? O and P. So here's the O spot, and here's the P spot. What can you tell me about the P spot? It's already taken, right? The nitro is there. Okay, what is the nitro directing to? Meta. So, and it's meta to it. So what spots are those? This one and this one. Okay, so what do you think the Br2 and Fe is going to do? It's going to put what on the ring? A bromine, and where is it going to be? One of those 2 spots. That makes sense? See how we did it? You just got to kind of logically go through it. It's really pretty logical. All right, let's look at this one. Up at the top, we have a T-butyl group, and what is it directing to? Well, what kind of group is this? It's an alkyl group, so it's OP, right? Okay, so what spots is it directing to? O and P. And what can we say about the P spot? It's taken. All right, what is the methyl directing to? Its own O and P. And what can we say about its P spot? It's taken. Okay, what can you tell me about a methyl versus a T-butyl? They're very different in size. So who's going to win? The one on the bottom, the methyl, because it's littler. Okay, what are we going to put on the ring? What does HNO3 and H2SO4 do?
NO2.
Yep, and NO2. Okay, so where is it going to be? There we go. It's going to be one of these spots, the blue spots. So little methyl beats big T-butyl. Because this is too bulky, it's blocking those spots. Remember when you made para-ditbutyl benzene. You got 0 ortho ditbutyl benzene because the T-butyl group was blocking the ortho spots. So your incoming group went para. Okay? Remember why you added 2 T-butyls instead of just 1?
It makes it more reactive.
Because it makes it more reactive. Okay, the T-butyl benzene is more reactive than the benzene. You actually made T-butyl benzene, but then it quickly reacted. Okay, all right, now what about this one? I think about that one. Okay, so at the top we have, oh, they're both black. I didn't make them colored. All right, so I'll use purple for the top one. What can you tell me about that group? What kind of director is that? OP. Okay, so that means it's going to direct to these 2 spots and this spot down here on the bottom is out of there. It's already got a chlorine on it. Okay, what can you tell me about the chlorine down here? It directs to OP also. So here's the O's, and its P is also taken. Okay, so who wins? The top one or the bottom? Why are you picking the top one? Give me a reason.
Activating.
It's more activating. In fact, that nitrogen has a lone pair on it, right? Don't forget that. And it is an activating OP director. This one is a deactivating OP director. I wrote the P, honest. Okay, so what do we get? We get that one. Okie dokie. Making sense. Is it making sense? All right, now look at the bottom one. I don't know why both my methyls are blue, but they are. I'll make one purple. So this methyl up here is going to direct to what spots? The O's and the P's. Okay, so that's going to be these two and this one. Okay, I'll make this one purple. This one is going to direct to the same 3 spots. Do you see that? What is the product going to be? Is there any spot up there that you can rule out? The one between the metas, the metamethyls, metamethyl. Okay, so what are we putting on the ring? SO3 what? H, okay, and that's going to go to one of the ortho spots. Okay, do you see that they're the same spot? Do you see the symmetry in the molecule? If you put it up here or down here, it's the same thing. Y'all see that? Okay. So there's only one product for every one of these, like by far. Okay? Okay, now there are some issues with some of the reactions. Okay? So I have successfully avoided them. All right. Friedel-Crafts reactions. Remember that alkylations can rearrange, and we talked a lot about that one already. Okay? They do not work on rings with substituents that are stronger deactivators than halogens. That would be all of the meta directors. Nitro, SO3H, CO2 something. None of them can you do a Friedel-Crafts alkylation or acylation on. Okay? All right, what about this one? They do not work on anilines and N-substituted anilines. So what's an aniline? NH2 on a benzene. Yeah. I'll draw one over here, a little bitty one. Okay, you could also have like N-methyl aniline. You could have the methyl on that nitrogen. Okay. The reason is because the lone pair on the nitrogen will complex with your Friedel-Crafts catalyst. Your Lewis acid catalyst in the Friedel-Crafts reaction. Ugh. Okay, so that turns this nitrogen, instead of having its lone pair there available to help stabilize intermediates, it is now a plus because it's attached to your Lewis acid. So you cannot do that. Okay, so those don't work, which is kind of a bummer. Okay, there are some limitations on nitrations as well. Anilines cannot be nitrated. So anilines are kind of the trouble shot. Okay, the NH2 substituent is oxidized by the nitric acid and can blow up. It's minor. So because of that, we don't nitrate anilines. If we wanted to make a nitroaniline, we would do it another way, or we wouldn't do it at all. We would say, c'est la vie. Okay. Okay. Now, you can react on the alkyl substituents on a benzene ring. Okay? Free radical substitution at the benzylic position. I already reviewed this one, Br2 in H-nu. But you can also use NBS. Do you remember NBS? Are you telling me you don't have the slide? You're looking for it? Am I out of order?
Yeah.
All right, did you find it? Okay. All right, sorry about that. Did you find, what page is it on?
I don't know.
Oh, it doesn't have page number. All right, it's there, just
It's
feel that.
It's like the third to the last slide.
Okay, she says third to flat. Everybody find it? Okay. NBS with heat and peroxides usually, or this is that other one, Br2 or Cl2 with heat or H-nu. Usually it's written H-nu. You can even write the benzoyl peroxide and heat. You have to have an initiator usually in these. All right, what it will do is it will put a bromine on, using free radical, it'll put a bromine on the benzylic position, okay? We'll see what it did. You probably have the little reaction written there, no products maybe. Oh, I didn't even have the MBS in there. Gosh. Okay, don't be surprised. You will often see NBS is written on the arrow. You'll see that in your homework and such. You'll get your homework open today. I had a lot of homework to get open. Okie doke. Smoky. What? You're still writing?
Yeah.
Okay. I have no idea why I changed the order on you. Okay, this is substitution. Okay, you can do nucleophilic substitution at the benzylic carbon. So what is the nucleophile in this reaction? Are you writing it down?
Mm-hmm.
What's going to be the nucleophile? What do you think? What's the leaving group? What? Leaving group is the chlorine. So what's going to substitute for the chlorine? Okay, so can you figure out what you'd get? Looky there, we made an ester. An ester for Easter. Okay, what do you think the mechanism? Okay, hint, it's a nucleophilic substitution. You got a 50-50. Did you know that? Okay, it's typically SN2. If you start substituting this carbon, it switches to SN1. Also, what can you tell me about nitro? What do we know about it? It's a deactivating group, right? So if you formed a carbocation there, would it stabilize it or destabilize it? If you're pulling electron density out of the ring, what is going to happen to a carbocation over here? It's not going to be stabilized. If you had this compound instead, and you were doing the exact same reaction, what is this group? An activating group. It could very easily go through an SN1 mechanism and make that benzylic carbocation that would be stabilized by the benzene ring and the OCH3. This is really messy. Okay. As you substitute at this carbon 2, that also makes it help stabilize the carbocation. So if you had two methyls there instead of two hydrogens, you'd probably be SN1 because you're going to make a tertiary carbocation. Make sense? Even though the nitro is there. Okay. Oxidation. What happens in these is you can actually oxidize the carbons attached to the benzene. Is that next? Is that not next?
It's already next.
Okay. Boy, I really switched it around, didn't I? I'm sorry. Okay, your commonly used oxidizing agents are potassium permanganate, that's KMNO4, and sodium dichromate, that's this one, Na2Cr2O7 in acid. Okay, you must have at least one benzylic hydrogen. So how many benzylic hydrogens does this first compound have? How many benzylic hydrogens? It has how many? 3, right? You have to have one. If you don't have one, it won't work. Okay, the entire alkyl group gets oxidized to a CO2H. So what you're going to make is going to be that. Okay, how many benzylic hydrogens are on this group and this group? This one had 3. How many does this group up here have? It has 1. These aren't benzylic. They're all another carbon away. Benzylic, remember, are next to the benzene ring. Okay, so when you do that one, what are you going to get? This is going to become a CO2H, and this is going to also become a CO2H. Those 2 methyls just go bye-bye. They're just gone. I think I even had yields. Yeah, look at that. They only got 45% on that. Sad, isn't it? Okay. What if I had a T-butyl group on? How many benzylic hydrogens are on a T-butyl group? None. So it does not get touched. Okay. So look at this one. Okay, so you got this page? All right, so you look at this one. What's going to happen up here? What's going to happen up here? I'm going to get a CO2H, but what's going to happen down here? Nothing, honey. Okay, so you see the difference. It doesn't matter if there's 1, 2, or 3 benzylic hydrogens. You get the same thing. And so like, look at this one. That one has an OH on it. Do you remember when we did chromium oxidations of alcohols to ketones? Guess what happens on this one? We don't get a ketone because we have, oops, oh, sorry, because we have a carbon that's benzylic. So what are we going to get? A CO2H up there. Okay. What if somebody said, but I wanted to do it. So guess what? Somebody found a way. Don't you love that? All right. So notice what the reagent was. MnO2. Not as oxidized as KMNO4, okay? That manganese has a higher oxidation state than MnO2. So that's how come it stops it. Okay? So if you want to get a ketone from a benzylic alcohol, you still have to have the alcohol, y'all. This wouldn't do anything to like this compound up here, okay? It wouldn't do anything. But if you want to get the ketone, then you use the MnO2. Okay, it's a different oxidation state to start with. I don't know of a chromium alternative. That might make you happy, I don't know. All right, now we're going to use everything that we just talked about, and we're going to make these things from benzene or toluene and any necessary organic or inorganic. Okay? So let's look at the very first one up. Okay, so we're going to start with benzene or toluene, and what do we have to put on our ring? We have to put on it this, and we have to put on it this. Okay, what can you tell me about this group? Do you know how to put it on? Use a Friedel-Crafts acylation, okay, and do you know how to put this group on? Bromine, and you have to have a Lewis acid catalyst, so don't forget your Fe or FeBr3. When you put Fe in bromine, remember it makes a FeBr3 in C2. That's only different. It's the same thing. Okay, so which group do you think you want to put on the benzene ring first? This group or this group? What do you think? The bromine? No, someone's saying no. Okay, you want to put this group on. Okay, why? What? Oh, no. What kind of director is this group? It's a what? Meta director. What kind of director is this group? OP. What are the two groups to each other? Meta. Does that make sense? How we like thought it out. They're meta to each other, so we're going to put the meta group on first. Okay, so I have to insert a blank page. Now, do you want to start with benzene or toluene? Y'all know what toluene is, right? Okay. What are we starting with, you think? Benzene. Okay. What am I going to put on first? Okay. Do I need anything else? You need your, yeah, you need that Lewis acid catalyst so that you make your intermediate, which is called a psyllium ion. Psyllium ion. Okay, so what do I have now after that step? We're not going to do all the mechanisms. We're just going to write out what we get. Okay, so here's my benzene. Maybe it's not wanting to connect. Okay, and then what do I have on my benzene now? Okay, and then what am I going to add? Br. Sure. Okay, and what do I get? My bromine is meta. Okay, so far so good? Okay, I'm going back. Okay, let's look at the next one over here. What do I have on my group, on my benzene? I have a nitro, and I have this group. Okay. What can you, which one do you think you want to put on first? Which one do we want to put on first? Why? Because it's a meta director. What about the nitro? It's a meta director too. How do you put this group on down here? What is the reaction? Friedel-Crafts acylation. Okay. Why do we have to do it first? Remember the limitations. It won't work on the nitro. Okay, that's why we went over those. All right, so we're going to start with good old benzene. Okay, now what do you need to put that acyl group on? What are our reagents going to be? What?
Yeah.
Okay, make sure you have 3 carbons, not 2, 3, okay? And then what goes down here? All right, so what did we make? Maybe. Okay. And then what are we going to add? How are we going to put the nitro on? What are the reagents? HNO3 and, all right, so what do we get? Our product. All right, does everybody see why you have to put the Friedel-Crafts acylation, that acyl group, on first before you do the nitro group, okay? You could wait, Taylor, until I finish. Okay, so there's 2 more on that page. Try to do the other 2. You got to think about all that other stuff we talked about too to help you get through that. Okay, and I'll do those first thing on Wednesday. Okie dokie.